I'm Bill Newman, the owner and founder of RNAS Remediation Products, and I'm going to talk a little bit today about anaerobic bioremediation and using electron donors and other products for in situ groundwater treatment. So I like to start with a chemical reaction that everyone intuitively understands. I'm sure you've all seen the fire triangle. And in order to maintain a flame, we need to have fuel, which is our electron donor. We need to have an oxidant, in this case oxygen from the air, and then we need some energy to get that chemical reaction going and keep it going, and that's heat. So if we bring all three things together, we can continue the flame. It makes more heat, and as long as there's oxygen and fuel, it sustains the reaction. So let's look at what microbes can do. It's a little less intuitive for the kind of treatment that we're doing because the contaminants are actually the oxidant, in this case trichloroethene, and then we provide the electron donor, the food or the fuel, which in this example is emulsified vegetable oil. The microbes provide the enzymes to lower the activation energy and the initial cellular energy to get things started. And if all goes well and we keep the microbes and our electron donor and our contaminant in the same place at the same time, we make more microbes and continue to reduce that trichloroethene to harmless ethene. So let's look at some contaminants that are suitable for anaerobic treatment. Certain oxidized metals like chromium-6 are very easy to treat. They can't be destroyed, but that they can be reduced to less toxic, less mobile compounds like chromium-3. Nitrated explosives like TNT, RDX, HMX. The microbes can utilize the nitrate as a electron acceptor and reduce those to less toxic compounds. And then chlorinated solvents, the microbes can remove the chlorine and use the chlorine to produce chloride as an electron acceptor and reduce those compounds to less harmful ethane or ethene compounds. So how do we solve the engineering problem of bringing the contaminants, the electron donors, and the microbes together? That can be a challenge. One of our biggest problems is that we often don't have a clear understanding of where the contaminants are localized. So it's very important to do a good site assessment. We need to know where the contaminants are. We need to know if they're mobile. And then we can begin to plan how we can deliver our electron donors, perhaps microbes and buffers, to produce the optimal environment in situ where the contaminants are. So how fast can we do this? If we put everything in a bottle in a lab, it can happen pretty quickly. Here are two microcosm studies with 10 milligrams per liter of tetrachloroethene. The microbes are able to reduce that much PCE to ethene in a month or less in the one case. But that doesn't really happen in the ground for an in situ treatment, for a couple of reasons. One reason is the diffusion limitations. We often have a complex geology where our injected materials tend to go in the more permeable sand layers, as illustrated here, and then the contaminants are rapidly treated within those sand layers, but the contaminants that are trapped or stored in the less permeable silt or clay layers can then slowly diffuse back out and recontaminate the treated sand layers. And this is one of the reasons why it's very important to have a electron donor with good longevity, so that one injection can last for years and allow time for those contaminants to come out of those storage zones. Another reason we want longevity is that it's simply not practical to inject our amendments into all of the contaminated pore space. So even on a source area or a small site where we might use a grid approach, it's unlikely that we're covering more than 10 or 20% of that pore volume with our injection event. So the contaminants are going to have to flow by advective groundwater flow from where they're at initially into those treated zones. And then very commonly when we have a large dilute plume, we use transects of treatment where we inject our EVO or other amendments to create biologically active zones that the contaminants then have to move through very slowly. So groundwater flow may take years to move through the barriers, and the contaminants often have a retardation coefficient that makes them move more slowly than the groundwater. So multiple barriers and multiple years are very often needed to treat a large plume. So our most basic form of electron donor is molecular hydrogen, which is produced by the fermentation of our EVO and other products. Different types of microbes require different concentrations of hydrogen. This is some work done by Frank Loeffler back in 1999, looking at the absolute minimum concentration of hydrogen to sustain these microbial communities. As you can see, the nitrate reducers require very low concentrations, so treating nitrate as a contaminant is very easy. The dechlorinators, again, well under 1 nanomole, 0.3 nanomoles, so again, very low. Sulfate reducers require a bit more, and some of the sulfate reducing microbes are also dechlorinators. And then the methanogens and the acetogens, which are competing microbes that don't necessarily help us treat our chlorinated solvents, they require much more hydrogen. And why that's important is that if we can maintain the hydrogen at low and steady concentrations with an electron donor like our EVO, and in the case of Yang and McCarty's reference, they recommend between 2 and 11 nanomolar concentrations, we can have maximum dechlorination activity, but minimal production of methane and acid. And our EVO is ideal for that. So slow release donors such as EVO can allow for biostimulation for several years with a single injection. There are a variety of contaminants that can be treated, but in the case of the chlorinated solvents, that slow and steady release of hydrogen to maintain low but steady concentrations of hydrogen is ideal because it stimulates the desirable microbes without stimulating the microbes that are competing with them. So let's talk a little bit about the mobility of oil and water emulsions. There are two primary methods that oil droplets can be captured and retained. One is filtration, where if a large droplet tries to go through a smaller pore space, or it gets physically trapped in a little corner between soil particles, it's physically trapped. The other is interception, where an oil droplet touches a soil mineral surface and then it's attracted to that surface by an electrical charge or van der Waals forces. So it sticks and stays. And filtration primarily works on larger oil droplets. There are a lot of filtration models out there. One by Zhu et al. Basically predicts that if the ratio between the mobile particles, being the oil droplets, and the soil particles, being the soil matrix, is less than 0.008, there should be little, if any, capture by filtration. So what does that mean in terms of our products? If we have a small droplet EVO like the 60E that we manufacture in Brazil, unless the soils are a silt or smaller, about 60 microns or smaller soil particle size, there's very little capture by straining. We still have absorption by interception, but essentially no straining. If we want higher retention, we can use a field-produced emulsion like our HRO product, which averages around 5 microns. And we now see straining capture when the soil particles are on the order of 0.5 millimeter or smaller. So let's look at the 60E product. This is the primary product that Humo manufactures and distributes for us in Brazil. It contains 72% fermentable material. It's primarily soybean oil, 60% soybean oil by weight. It also has 6% ethanol as a preservative and a fast-release donor. And then, of course, the balance is water and surfactants that stabilize the emulsion. The oil droplets are very small and uniform because they're processed in a factory with a very high shear mixer. Essentially, all of the droplets are under 1 micron in size. And because the oil is such a efficient source of hydrogen, 1 kilo of the 60E EVO produces 2.5 times as much hydrogen as a kilo of molasses. Let's look at the HRO product. The HRO is an oil and surfactant blend. It's 100% fermentable content, 90% oil. When mixed with water and gentle stirring, we produce an emulsion with 1 to 10 micron oil droplets, which gives us better retention in sandy soils or fractured bedrock. And because it's mostly soybean oil, and soybean oil is a very efficient source of hydrogen, the HRO product contains 3.5 times as much hydrogen as a kilo of molasses. So let's look at a common problem called the DCE stall. Chloroethene degraders, there are many different microbes that can reduce tetrachloroethene and trichloroethene to dichloroethene. But there's really only one group of microbes, D. helicocoides mccartyi, that can reduce dichloroethene to vinyl chloride and ultimately to ethene, which is the harmless byproduct that we want. So when those microbes are not present at a site, we will see a DCE stall. More commonly, the D. helicoides microbes are there, but the pH is lower than optimal. And ideally, we want to maintain a pH of 6.5 or higher. For sites that don't have the microbes, we can add a bioaugmentation culture, like the SDC9 culture. We use this very commonly in the US and elsewhere in the world. We don't currently have it registered in Brazil, but we are working on getting a registered culture for the Brazilian market so that we can make that tool available. So let's look at a microcosm with the full strength D. helicocoides culture, SDC9. It has a very high cell density of about 1 × 10 to the 11th cells per liter. And we grow those microbes at pH 6. So in the case of treating 10 milligrams per liter of PCE at a pH of 6.1, you can see we get all the way to ethene in a little over 20 hours. If we lower that pH to 5.5, it takes 10 times as long. And if we were to lower it to pH 5, it wouldn't happen at all. We would stall at DCE. So what is our solution for that problem? We make and sell a colloidal calcium carbonate buffer in Brazil called Neutral Zone. The product consists of small micron to submicron calcium carbonate particles, and we're able to inject those and make them mobile during the temporary circulation or injection, but they don't move with advective groundwater flow. And that's important because if we inject a soluble buffer like sodium bicarbonate, it can move out of the treatment zone even if the contaminants and the EVO are retained on the soils. So the calcium carbonate itself is relatively insoluble in water, but when acid is present, it releases bicarbonate buffer. So it acts as a slow release buffer to release bicarbonate when needed, so that one injection can last for several years. So let's look at how we can apply emulsified vegetable oil. The oil and water emulsions have a low viscosity, so that they're a lot like water in terms of viscosity, very easy to inject. We typically inject 1 to 5% oil by weight, and we can use direct push injection tools. I prefer a top-down injection approach. Most direct push injection equipment is limited to a depth of about 30 meters, so we may need to install wells. We can do direct injections into wells, or we can do a temporary circulation between wells to carry that EVO laterally a greater distance, and of course install fewer wells, which saves us money. Once the EVO is in place, that circulation can be shut down, and then those biobarriers can stay active for several years. So let's look at a site where we use that approach. This is Dover Air Force Base, and you can see the gray lines on the map indicate that there are a lot of roads and buildings. So this is an active Air Force base. We can't just punch a hole in the ground anywhere we would like, because we don't want to disrupt the Air Force Base activities. This particular area, Area 6, is a relatively large plume. You see the scale bar in feet, 1,000 feet. The two red lines that are transects across the plume were emulsified vegetable oil biobarriers installed by direct push injections. The green lines consisted of wells spaced approximately 15 meters apart, and they use circulation alternating with injection and extraction wells, circulating in one direction for a week or two, and then reversing the flow in the other direction, and then shutting it down for several years at a time once the EVO had been installed. The geology was a silty soil, a silty sand, and so groundwater flow was relatively slow. You can see this figure shows the contaminants, the TCE concentrations in June of 2006, and then many years later, in 2015, the contaminants have had time to move through the barriers, and you can see we removed about 99% of the contaminant mass with those biobarriers. The original pilot testing used another product from a competitor, and they found that some of the wells were backing up and clogging because of the larger, less mobile droplet size. When they used our product, that problem went away, and ultimately between Area 6 here and Area 5, the Air Force used about 750,000 kilos of our EVO product to effectively treat both of those plumes. So let's look at a simple direct push treatment example. This is a site in Northern California where they wanted to redevelop the contaminated property as quickly as possible. The plume has kind of an odd shape because of the braided sand channel old stream bed geology, so that's why we have this red hourglass shape with the highest concentrations. The pH was a bit low, so we required both buffer and our EVO. And you can see here the red shaded areas are above 1,000 parts per million, or parts per billion, excuse me, and the blue is less than 10 after treatment. With the grid approach, you can see there's only 2 locations that are slightly above that 10 parts per billion. In total, there were 163 injection points spaced on about a 5-meter grid. The initial pH was below 5.7, and we averaged a pH of 6.7 and maintained it for several years after injecting the neutral zone. So let's look at an example site with fast flow where we need the higher oil retention. This is a site in the Midwest which had a plume about 1,650 meters long. The advective groundwater flow was extremely fast, about 2 meters per day. Initially, they did treatment with pump and treat and emulsified zero-valent iron on site, but of course there was a long dissolved plume in the off-site properties, and for that reason we looked at using an EVO biobarrier approach. This was pilot tested in 2011 with the HRO product, and it worked very well. So they then installed a series of biobarriers down gradient between 2018 and 2023. In addition to the HRO, we used a little bit of quick release donor, a oxygen scavenger, and the SDC9 bioaugmentation culture. So this is what the plume looked like in May of 2017 after the pilot test, but before the full-scale application. You can see it's a very long, narrow plume because of the fast advective groundwater flow. And then the next figure shows color-coded lines showing the biobarriers, the green ones installed in 2018, the red in 2020, the blue in 2021, and the orange most recently in 2023. So obviously not all of these biobarriers have had many years to allow the contaminants to travel through them, but you can see we've already knocked some big holes in the plume and we're effectively reducing the contaminants. It's a little bit harder to read, but you can see the areas indicated where 90 to 100% of the TCE has been reduced. The yellow coating is where it's 50 to 90, and the orange is 32%. So very good activity, and because the HRO EVO lasts for many years, we anticipate that those biobarriers will keep going for years to come. So our Brazilian partners, Humoquímica, manufacture and distribute our products in Brazil. They also make products for export. We've been using their products in Europe and in South Africa. And we've manufactured a number of products. Primarily we manufacture the 60E, the HRO, and the neutral zone. And with that, I want to thank our Brazilian partners, Americo and Marcelo from Humoquímica, and also I want to acknowledge my business partner, Jeffrey Hansen, who helps us with business development in Brazil.